Okay, thank you for the introduction. And I would like to tell you about the research work that we have been doing for the last few years. This is a joint research with Professor Antonio Turalba, also ECS at CSO. All right, so there's a lot of work on sensing for robotics, sensing for inspection, and of course for different types of HCI applications. So you might, of course, be familiar with lots of activities in the vision-based sensing, for example, RGB or standard cameras or cameras with depth. There is also quite a lot of work on mechanical sensors. That's one of the areas that you can imagine that's developing quite substantially, and some decent amount of work on new optical sensors, for example, for sensing touch. Many of these technologies, unfortunately, have problems. So, for example, cameras or vision-based sensors, they really suffer from occlusion artifacts, and mechanical sensors are typically not very robust, not very scalable. So here we are going to see some of the technologies that we have been developing that address some of these issues. So we have been working for a few years on this, on new types of touch sensors. And we wanted to figure out what the right requirements for these sensors are. So the first thing is that the sensor really should have high density. It should provide high resolution touch force sensing capabilities. Second, it should be flexible. So you should be able to bend it. You should be able to wrap it around any type of object. And finally, it should be also robust and durable. So this type of sensors, if they are supposed to be used in industrial applications, they cannot work for 10, 20 minutes. They have to work for days, if months, years. And so they have to be, of course, very, very robust as well. So we have started with the first type of sensor like this, and this is a sensor that has 32 by 32 resolution, so decent amount of sensors, around 1,000 sensors. And as you can see, the sensors can be pretty much attached to any type of garment. So for example, you can build this kind of sensor, and you can attach it to a glove and get a glove that has force sensing capabilities. Here, throughout the talk, I'm going to be showing lots of images. So, for example, when you sort of see these kind of circles, you will see that the circles that have low brightness essentially means that there's no force. Typically, high values mean that there's some force associated with this, so just for you not to be surprised. How are the sensors built? Well, this is very, very simple technology when you think about it. You have conductive threads going in two different directions, and then you have a force-sensitive film. So it's a very inexpensive film that you can buy off the shelf, and everything is also laminated nicely, so it offers nice protection. So for each of the intersections of these two wires, of course, you will essentially get a force readout, because as you change the distance between these two wires, when you apply forces, of course, due to the electrical properties of this film, the resistance is going to change, and you are going to get a very different readout of the voltage. So this is how the data capture works. So as you can see, the sensor is nicely bendable. You can pretty much bend it any way you want this. You can also attach it to any type of glove in this case. So you would typically make it in the form of any shape you want. And then, as you can imagine, there are these electrodes that are sticking out. And here I'm just showing a simple image, a simple video that shows how a person that performs very complex tasks, in this case folding a paper plane, can essentially perform this task wearing this type of force-sensitive glove. And here you can sort of see in the image all of the force readouts as the person performs this task. So as you can see, already this is a nice capabilities. You can already record all different types of actions that human can perform. Okay, so we have, once we have built these sensors, we have looked at what, of course, we wanted to characterize them very, very carefully, and it turns out that you can sense a whole variety of different forces, starting from low millinewtons to newtons for each of these elements. And we have done very extensive testing over lots of cycles, so you can really use it for extended periods of time. So this is all good. You can, I think this is that type of technology that you can start really using and for different types of commercial applications. So now that you have already this type of sensing technology, you of course would like to figure out what can you do with this. And the most interesting thing that that you can sort of imagine is sort of start coupling these technologies with the modern machine learning tools and basically try to make sense of the data that you are capturing. So the first task that we have looked at is that once you can have this kind of sensor and you have a person wearing this kind of sensorized glove, can we potentially figure out what what a given person is touching, what kind of object is the person is touching. So can we figure out what types of objects a given person essentially is currently interacting with? This was the first time that computer systems could potentially try to make sense, to make sense out of the tactile information. So here we have created a data set of objects, in this case 26 different objects, and we have also captured interactions of people wearing this kind of gloves with each of these objects. As you can imagine, with this kind of sensor, you can really capture tons of data. So in this case, 130,000 frames was captured over the course of a day. And the next part was really, now that you really have that kind of data, can you potentially try to predict what, based on just the touch information, what kind of object are you interacting with? Obviously, people can do it very, very well. Can computers also do this? So this is an example from the data set. As you can see, a person interacting with a cup, right? As you can see, there are very, very distinct signatures associated with each of the objects, and as you can imagine, each of the objects is going to have quite a distinct signature, different types of tactile signature, and of course, people, even if you close your eyes, right, you can very easily tell what kind of object you are interacting with. Is it a cup? Is it an apple? Is it some other fruit? You can potentially tell this very, very well. So our task was to figure out can computers and machine learning models can they predict this type of information? Right, so as you can see, in order to make machine learning algorithms work these days, you have to get lots of data. So these types of sensors are perfect because you can really, really take tons of data interacting with different types of objects. And the first question is, how can you represent this type of information? And since our tactile information is so high resolution, there's obviously a natural representation for this data, and we want to borrow all of the stuff that we are doing in computer vision. So a natural representation here is to approximate all of the sensor locations on a grid and effectively build an image out of all of these little sensors. So you can now start thinking about tactile information in a very, very similar computer vision. People are really looking at the tactile at the images. So here, as you can see, some of the areas over there are not really covered by these tactile pixels, so you have to mask them out. And then the rest, so unused pixels are really essentially blanked out. And for the rest, right, you can start using very, very standard computer vision deep learning architectures that will tell you and you can sort of pretty much redesign these workflows to work with tactile data. In this case, you are really not really working with intensities as observed by cameras, but you are working with the forces that these pixels essentially sense. But the underlying sort of sensor, the underlying machine learning, well, architectures are very, very similar. So if you have built simple machine learning models, then this is how they would kind of look like. So as you can imagine, in this case, we are trying to build a classification system that takes tactile data in and predicts what kind of objects you are interacting with. Right, so in this particular case, this is at the end, you have a simple layer that performs multi-class classification and predicts a specific type of object that isn't the most likely. It's all of these things are in terms of probabilities. So if you were to look at the different types of objects, you would see that different types of objects are going to have, of course, they are going to produce, if you train them on all of the data sets that we have done, you can obtain pretty good accuracy. So if you really are trying to predict what kind of objects you are interacting with, this type of machine learning models can do it very, very well. So as you can see in this particular case, let's, for example, take as input the tactile signature of the smog, an interaction with the mug. As you can observe, the classification in this case is perfect, and the network, in this case neural network, can predict very, very well what the correct object. So what is really interesting, what's the first thing that we have really observed is that this type of information is really highly accurate, and we can build with this massive amount of data that we are capturing, you can really do very, very well in terms of classifying what kind of objects people are interacting with. So that was great, and here we were attaching the sensors to the human. But the next question is, can we instrument environments with these types of tactile data and with these types of tactile sensors? In this case, we have tried to build a carpet, which we called a magic carpet. But I think what's really interesting about it is that this is just a carpet that's made out of these tactile units. So same technology as before. In this case, tiles are made, these are 6 by 6 feet carpet. This is a 6 by 6 feet carpet, and the carpet is made of tiles, has almost 10,000 sensors. And in this particular case, pretty much we can capture very high quality information on people pretty much interacting with the environment. Why do we want to do this? This is potentially something that we can use as a new sensor that's placed in an environment, is not as invasive as standard cameras, so potentially much better I think that it has the overall, it will be a much lower barrier of entry for many users. You can put it pretty much in any type of environments, stores, if you want to put it in the house, elderly care facilities, and so on, but pretty much they can be done, can be placed anywhere, and of course the cost is extremely low. All right, so how does it work? As you can see, we have captured again lots of different types of activities, people performing many different types of activities on this carpet, and as you can see on the top, you see the videos of these activities. On the bottom, you can see the corresponding tactile data that's out of what's being captured. And it's not exactly obvious when you look at this data what is going on. I think at least the human would have probably a hard time to figure out what really is going on. Can we use modern machine learning tools to try to figure out much more from the environment? So how do we do this? Well, in this case, we'll use a computer vision camera as a teacher. So here we are going to put a number of cameras in this environment, and essentially in this case, the camera is going to be used as a teacher. The camera is going to tell me exactly what that person looks like, what the skeleton of this person looks like. This is a common vision task, and also what kind of actions this person is performing. So this is something very, very standard for which computer vision models already exist. But here we would like to capture this data along with the tactile data, and we would like computer vision to be the teacher for the tactile data. And here again, deep learning comes to the rescue, and we build a model where we use the information captured from the vision systems that tell us about all of different activities that are going on, and we have also the corresponding tactile information. Once we teach the model, once we teach this model, we can remove computer vision cameras, and now the only thing that we have left is just the tactile carpet. But we want to sort of see how much of this information essentially is being retained. So the first task was single pose, a person pose prediction. So in this case, we wanted to really figure out how well can I predict the pose of the person. So as you can imagine, the lower body we can do very, very well. However, if you look at predicting of the upper body, you have slightly more errors. And it's kind of makes sense. Basically, whatever you have in terms of the lower body motions, I think you can sort of try to figure out what that motion is, what that pose is. But when you are talking about upper body, it's becoming much more challenging. So this is how the system works in action. As you can see the tactile frames here. This is what a carpet observes, and the ground truth is the data that is reconstructed from a computer vision sensor. And here you can also see a prediction from the tactile carpet, and it's really, really good. If you kind of look at it, I think that overall there's very little difference between the ground truth over there and the predicted pose. So that's really great, and you can, if you really capture tons of data, lots of training data, you can really do extremely well. So what is really interesting and maybe a little bit surprising here is that this type of tactile carpets can be really useful to predict, for example, pose identity of the people that are interacting in a given environment. You can also classify different types of actions. As you can see, you can get, so for example, things like whether you are sitting up, or whether you are squatting, bending, and so on. If you're just interested in classification of the action, you can do extremely well. These are very high classification rates for these actions. And you can also work with, this also works with multiple people. So if you really work, if you work in the system, maybe the crew can play the video here if possible, but this also works very, very well on the multi-person pose estimation. You can have multiple people here as well. Typically, I would have a video here that plays. Unfortunately, I cannot play it right now. But overall, this doesn't matter. You can work. This type of carpet can be deployed in a facility where you can have many people that are walking. It's going to track different people, observe what they do, classify actions of the people, maybe even figuring out what the identity of the person is. So there's really lots of potential, lots of things that you really can do with these types of carpets. And what is really interesting is that they are much less obtrusive in terms of being there. All right, so we have seen already two different applications of these carpets, and we have looked at what's good about it and what's bad, and we really liked the high resolution. We really liked that they were extremely inexpensive, but there were a few things that we were not so happy about. So the fabrication or manufacturing of these sensors was pretty much manual. So the students were spending lots of time making them. We started automating this process as well. What we didn't also like is that the stretchability and the flexibility of the underlying fabrics that we were building. And the fact was also that the sheets were flat. So you could pretty much only do things that they're relatively flat. So with the new approach that we have designed, we really wanted to try to move to completely automated fabrication. So these types of sensors can be made at scale. We would like to make them stretchable and flexible, and we would like them to really work with arbitrary geometry. So here's our process. We use manufacturing of these sensors using knitting. And this is a whole garment knitting. This is a technique, if you that's we use to manufacture socks. Pretty much all different types of mass manufactured garments, they are all used in the production. The idea here is that we have a special types of fibers. Some of the fibers are piezoresistive. They are coated. These are conductive fibers coated with piezoresistive coating, very inexpensive as well. And basically, you have a few of these fibers, and whenever these special fibers intersect, when you apply that pressure, you will see as they start touching, the distance between them starts being reduced, and you are going to get a nice readout of the underlying information. So pretty much the same functionality as we have seen. We have done again, lots of different evaluation strategies of how this really works in practice, and it works surprisingly well. It has very comparable quality in terms of the fibers that we have done before. And you can pretty much automatically build a whole range of different types of garments. So in this case, we are building, again, tactile gloves. So these are the gloves that are completely automatically manufactured. They can be manufactured at scale if you would like to. They are inexpensive, and as you can see, they provide very similar in quality information to what we have seen before. Here you can see a tactile vest. So this is really great for any type of human-computer interactions, for any kind of health monitoring. So as you can see over there, we have also developed special calibration procedures or data correction procedures. The original data from the sensors is slightly different for each sensor. So we developed, again, machine learning solutions that allow you to calibrate the data from these sensors, that they come all very, very nice and clean. And as you can imagine, there are many possible applications for these types of sensors. They can be really nicely integrated with any type of garment. And this is yet another application. Imagine having special types of intelligent socks. And these socks are going to tell you everything about what you do, what kind of activities you are performing, how you are doing. So here, as you can see, we have these types of socks. And just by measuring pressure on these socks, you can estimate what kind of action you are performing, and probably you can infer many more information about this, about your health, and so on. And as you can imagine, you can also augment current robots with additional skins, tactile skins, and to make them safe, much safer than they are today. So in this case, any type of commercial robot can be instrumented with this special garment, or you can almost think like a special clothing for robot that can be designed to any type of geometry. And as you can see now, all parts of the robot have this pressure sensing capability. So, for example, this might be very, very important when humans interact with this robot. Whenever there's potentially some collision between the person and the robot, you can immediately have a response. But of course, I think there are also quite a lot of other possibilities here. Here, we are building these extra skins for different types of grippers. So we have designed a system where we can build any type of robotic grippers, and then later on, we can instrument these grippers with specially designed sensors. So as you can see, we can, and with this kind of additional sensors, you can, of course, perform a tactile-based feedbacks for robotics. So typically in robotics, you have a control policy that tells you what kind of actions you should be doing. And here, the tactile information can be used directly from the sensors, and it can provide very useful applications for many different types of course, interactions between humans and robots. So what are the next steps for us? Of course, we are going to be exploring many different types of applications that I already have seen. And so I think the most interesting applications probably are in the health space and well-being space, but also lots of applications. There are lots of very interesting applications in robotics. How do you really use it for different types of robotics applications and of course, for human-robot interactions? I just would like to end the talk with figuring out that really here we would like to also build systems that try to understand humans. And I think there's, of course, much more to understanding humans than just the touch. So here we are building the next types of systems. And I have to, of course, tell you that this is very, very crude. This is really very much a work in progress. This is an ongoing work. We really would like to start building systems that can do very, very comprehensive capture of different types of activities. And this can have many different applications for studying the people at the workforce, or even trying to figure out how to perform the actions. Optimally, for example, if you can have an expert performing a given action, and then you can study how the expert is performing the different action, the different types of actions, and then use it for the training purposes for a less skilled worker. So here we see, you can see that we have a motion capture system, wearable motion capture system that tracks the joint locations. We also instrument the system with the gaze tracker, so we also track what type of scene elements the given person is looking at. So in this case, as you can see, there's a gaze tracker that also provides first-person view of all of different activities, so you know also what the person is looking at. Similarly, you have the gloves, the tactile gloves. The gloves for figuring out, of course, how the person is interacting with the environment, and of course, tracking of the fingers and the hands. So here is some very simple setup that we have built. In this case, we have built a simulated kitchen environment. We also have a few extra cameras that observe this environment. And this really allows us to start building very comprehensive data sets of all of the difficult activities at house that for example, the person can do, and for example, that are not really accessible to current robotic systems. We would like to understand how humans even perform these actions. So for example, this is one simple task of opening the fridge. You can see all of the parts are being recorded, tactile information, motion, interaction with the environment, and so on. And here's another one. This is what's happening when a person's organizing tea bags. So we are really in the process of building right now a very, very comprehensive way of building this kind of actions and data set of these actions for many, many different actions. And of course, I really think while we show some examples of tasks at home, this can be, of course, done at factories, studying how the workers perform the tasks in factories, offices, and so on. So here, this is the summary of what I have shown you. I hope I have convinced you that high-resolution tactile sensing systems and hardware are really possible, and you can really start building them, and these systems are useful. I hope I convinced you that you can really couple those with machine learning workflows, and that can be used to make sense out of the data that we are capturing. And finally, I hope that there will be some of the applications that I have shown you, that some of these applications are going to be really done in the real world, and hopefully many others will follow and find even more different applications for these types of systems. With this, I would like to end and thank you, and I hope to answer some of your questions. So should I answer this? All right. There's multiple ways to pick up a cup with the same hand shape that would register different contact points or looks like something else. Is more data enough to differentiate what's being picked? So overall, I think we typically, first of all, we don't typically use just one frame, but we use a few frames of tactile frames. And what we have noticed that they are indeed highly discriminative. So you can really predict very well what types of objects you are interacting with. That said, if the objects in your data set, in your classes, are very similar, for example, if you have, let's say, an empty Coke can and a full Coke can, generally the tactile signatures might be quite similar. So for similar objects, these signatures might be similar, and the algorithms absolutely can make some mistakes.